Let's start with doing one of these problems. This is it's a second order partial derivative that we want using the chain rule. So we have to take a look at the first order partial derivative probably first, where f is a function of x and y, and then x and y are both functions of r and t, r and s. And then they want this thing, which is the partial of z with respect to r and with respect to s. Actually, with respect to s first. So partial with respect to r of the partial of z with respect to s. So we need to find out what this one is first. So this is going to be a partial of z with respect to s is a partial of z with respect to x, partial of x with respect to s, plus partial of z with respect to y, partial of y with respect to s. So we don't have a function for z or f. So we're going to have to keep that the same, but we do have functions for dy or dx, ds. We do have x as a function of s. So we could do that off to the side here and say that partial of x with respect to s is equal to 2s. Partial of y with respect to s is equal to 8r. So now we have the partial of z with respect to x times 2s plus the partial of z with respect to y times 8r. Now it gets a little bit more complicated because now we have, it seems like a function of x and y and r and s. So it looks like the partial of z with respect to s is a new function that we have that would sit on top of our molecule chain. And then this is a function of x and y, but it's also a function of r and s. That's where it gets a little complicated if you don't do all the full substitution. But x and y are also functions of r and s's. Wow, that looks all complicated now. What? And we want... Does it look like Satan now? We do want the derivative of this thing with respect to r, so eventually this is what we want. It looks like we have several paths to get there. Wait, do we want to do it this way? Now, go ahead, ask the question.
So for the initial, what you was asking for from the very beginning, the second partial with respect to z, and then it has it all over partial of r and partial of s.
Yeah.
How exactly did you
So this is how you would read it.
Just doing our own.
Yeah, so it's a partial with respect to S first, and then taking the partial of that with respect to.
I got it. Okay.
So I don't know if we want to go through this way. Let me scratch this and take a look at this. I think we essentially want to take the derivative of this thing with respect to R. Which is the derivative of this thing with respect to R. So let's see if we can do it like this instead. Let's cross this out. And now, let's see. We need to handle these two derivatives, and this is probably where I want to take a look at dz dx as a function of x and y. And again, a function of r and s. So this one doesn't look so bad. So if I want the derivative of that with respect to r, and this is just a constant with respect to r, right? So let's see if we could do it this way. We want the derivative of this thing with respect to r, derivative of this thing with respect to r, times this. So this will just be constant 2s. And then now let's take the derivative of this thing with respect to r. So the derivative of this is to take the derivative of this thing with respect to x. Can you see that? It's the derivative of this thing with respect to x.
Well, that would be over one.
So this will end up looking like d squared z dx squared, and then dx dr, and then now we want d z, the derivative with respect to y of dz dx. And then this is dy dx, dr.
Why is it dx again? Oh.
Because this is your function.
Gotcha.
All right, so let's write this derivative down. The derivative of this thing with respect to, this is d squared z dx squared times dx dr plus d squared z dy dx times dy dr times this constant. Now the next one, dz dy, it's also going to have something similar here. dz dy, that's this thing now. I want to break this down into a function of x and y, and then function of r and s. And so that derivative will involve the derivative of dz dy with respect to x. So that's d squared z dx dy and then dx dr, which, by the way, we have this information up here, right? Plus this other side, the derivative of dz dy with respect to y. So that's d squared y, d squared z, sorry, dy squared. And then the derivative of y with respect to z, or with respect to r. Derivative of y with respect to r. dy dr. Yeah, so this is a product rule now. We have to be careful about this one, because unlike the one before this, we have this is constant, and this is now a product rule. So it's the derivative of the first times the second. So this is where the 8r comes in. Plus the first times the derivative of the second. So this is your product rule for this derivative here. So we have dx dr, dx ds, dx dr is, this is x is a function of r, so dx dr is equal to 2r, and then I don't know if we need this, but dy dr is equal to 8s. So we can fill in some of those blanks. We have partial of z, partial squared z, partial x squared, and dx dr is 2r. Partial squared z, dy dx, and assuming that this is a nice function, dy dx, dx dy are going to be the same, and we'll deal with that later, times dy dr is 8s. So this is in parentheses times 2s, so we need to multiply that out, plus d squared z dx dy, and then x with respect to r, plus d squared z dy squared, derivative of y with respect to r. Oops, there should be a plus. Oh, there's a plus here. 8r. And dz dy, you can't simplify that anymore. Times 8. Okay. So we just need to distribute. And then probably combine these two, because the dy dx and dx dy are going to be the same. So let's distribute d squared z dx squared times 4 rs plus d squared z. Now dx dy, dy dx will be the same. So let's figure out what the coefficient is here. So this is going to be 16s squared, and this is going to be 16 SR. R squared? R squared. because it's this one. So it'll be 16 s squared plus 16 r squared. And then this term over here is the d squared z dy squared, and this is a 16 sr. And then this one didn't get to get combined with anything because it's still a dz dy times 8. Which one?
16.
Oh, 64. Okay. Is that right? I guess we could check. Oh, there's no responses. Then it'll give us another different problem.
Yeah, but the output, the numbers will just be a little off, but the format should be the same. Yeah, it's just put ones and everything, and then just grade this.
So wherever there was an 8, you divide by 4. Divide, I don't know what that means. Divide by 4. So r times s.
4rx.
Okay.
The second one. 4s squared plus 4.
Oh, but this is the y, the one with the y squared.
Yeah. Okay.
So the one with the y squared is 64. So we got that by doing 8 times 8, right? Just be 1?
4?
4?
Because we have to divide it by 16, no? Because it's 4 for each 8.
So 4r squared?
Plus 4s squared. That number.
This is the r squared plus s squared? Is it 2 or just by itself?
No, it's 4s squared. And 4s. And then
I think just get it wrong and then show answer.
You don't put anything on the front.
It's the show answer.
Yeah, like 4.
it's 4, the first one is 4.
It has to be
Both of them.
No, this one was wrong. It was 4, it was wrong. You think the answer will help you?
No, I think.
No, I mean, so confirm our answer.
If you put
It's, yeah, 3x.
Oh, rs.
Yeah. Divide by it.
This is a 4 also?
Yeah, whatever. It's not squared.
rs also?
Yeah.
So,
No, that is right.
I guess it is wrong. I wanted to see.
So it's just everything divided by scale.
I know it's not expected to be this in a test.
no. This is not a test question.
This even extra.
No. This is just a question.
The tape is 0.
So what type of question? It's a test.
You won't have a question like this on the test. I mean, this is too long to deal with. All right, let's get started with our new stuff. So max and mins, we're going to do the second derivative test, and I'm not sure about the absolute value, absolute max and min, but maybe we'll just talk a little bit about it. But I'm more concerned about the second derivative test. So just to remind you of what happened in Calc 1, we found maximums and minimums by finding critical points. You remember doing that? Zero or undefined is usually what we look for, critical points. And then we have this thing called the first derivative test. First derivative test. So you find out where your critical points are, and then you check by you doing the first derivative, you would check whether something's increasing or decreasing. And then you know that the slope is zero or undefined at those certain points, that if they go from increasing to decreasing, we know it's a local max. If we go from decreasing to increasing, we know it's a local min. But there's this thing that we had that we didn't use very much. Where you look at the critical points themselves, and then you check whether they're concave up or concave down. And then if they're concave up, you know it's a maximum. I'm sorry, if they're concave down, you know it's a maximum. If it's concave up, you know it's a minimum. So that's the second derivative test.
Setting the second derivative equal to zero finds you the point at which it's shifting from concave up to concave down, or vice versa.
Yeah, you can find changes places where the graph changes concavities. But the first derivative test just goes from left to right, and then you try to see what the graph might look like, and then you could tell. Now, when we're talking about functions of two variables, this idea of the first derivative test doesn't make sense anymore. Because just like limits, there's many ways to approach the limit. There's many ways to try to approach the maximum or minimum. And so the first derivative test won't work. And so we'll rely on the second derivative test. All right, let's give some definitions for the max and mins, and let's see how this complicated looking definition actually, how this works. So we're talking about functions of two variables here. Where f goes from R2 to R. A function of two variables has a local maximum if f of xy is less than or equal to f of ab, where xy is near ab. What? So what does that mean? So that means visually we could take a look at a point AB, And we could take a look at some points x, y. That's close enough to AB. Whereas if we put that value in to the function AB, we're going to get a certain height. And what they're saying is that if we put any other point like xy that's near AB, then that value would all be below. All these values near AB would all be below that other point. So any other value you pick, any other pair xy that you pick that's near AB will give you a z value that's less than this f of AB value. What? And not right below it, because if it's right below it, then it wouldn't pass the vertical line test. So it'll just be around it. So all these points are on the xy plane in the domain xy. And then if you put that into the function, it'll all be below that. Below as in the height. Okay. And so the minimum is defined the same way. And it's local, which means at some other point in that function, maybe the graph will come back up higher again. But it doesn't matter because we're not concerned about things that are far away. We're just concerned about things that are close to it. All right? I think if you can understand that, then that's great. It gets really mathematical for the couple of people that are math majors there. You should really try to understand what this means. If you're not a math major, you don't understand it, we can just move on. So the next step is to find critical values. I didn't formally define critical values here, it looks like. The subscript means that's the first derivative with respect to x and with respect to y. And so in this case, the point AB is called a critical point. So it turns out that wherever you have the local max or local min, it turns out that your derivative is equal to 0 with respect to x and with respect to y. So that place where you have the derivative equal to 0 with respect to x and with respect to y is called a critical point. And unfortunately, finding the critical point is not easy all the time. It's easy sometimes. I guess everything's easy sometimes. But this is where we're going to start. We're going to start by finding the critical points, and then we're going to run it through what's called the second derivative test. Okay. So let's see if we can practice finding critical points first before we do the second derivative test. Do I have some examples?
Will it be inherently obvious when you use the second derivative test?
Say it again?
Will it be fairly obvious when you should use the second derivative test, or does one need to kind of determine after you try the first derivative test?
No, there's no first derivative test here.
Oh, okay.
Yeah. So, just to let you know, when we're dealing with higher dimensions, there's no first derivative test anymore. The first derivative test, you know, it's in 2 dimensions, so you're going from left to right, so you can see when the graph's going up and down. And that's fairly clear where you find our max and mins. When you're in 3 dimensions, you're talking about surfaces now. There's a lot of ways to get on top of the mountain. No, we're always going to stick with the second derivative. Let's do one of these problems. Number 5, maybe. I don't know. Hope it's not hard. Just finding the critical points. So example, let's find the critical points. First, find the derivative with respect to x. And then we're going to find the derivative with respect to y. And then we're going to set them both equal to 0. And the thing is that they both have to be equal to 0 at the same time. Well, this is the thing. At this point, you could do whatever you want or whatever you can, any way you can, to set them equal to 0. And you have to find values of x and y. Now, in this particular example, it turns out that they're both linear. They're both lines. And so there's going to be exactly one intersection. And then you can use systems of linear equations or whatever. But when you set them equal to each other, you lose something. You have one equation and 2 unknowns, and so you want to keep 2 equations. So one of the ways to do this is to solve for one of the variables in one equation and plug it in, basically the substitution method. Another way to do this is to possibly graph the 2 equations and then see if you can find an intersection. So in this case, it's pretty straightforward. Let's see, if I solve for y on the first one, and then put that into the y in the second one, and then solve for x, this would be 4, negative 3, x is equal to negative 1, x is equal to 1/3. Yep. So this is your critical point. And this seems like it's the only critical point in this example. So this is our only critical point. So if you have a nice graph, then you get one critical point. But chances are you're going to get something that's a little bit stranger, and it could take a little bit more information. But that's a general idea of finding critical points. Okay? We'll do a couple more examples later when we introduce the second derivative test. All right. Let's do the second derivative test. Second derivative test. So let me just copy the statement of the second derivative test. This isn't exactly what they have in the book. What they have in the book doesn't address the idea that sometimes you might get your d to equal to 0. So let's walk through this. Suppose the second partial derivatives of f are continuous in a disk, and suppose that fx at AB and fy at AB is equal to 0, so that AB is a critical point. Then we're going to define capital D Maybe we can call it the discriminant is equal to fxx evaluated at AB, fyy evaluated at AB, minus fxy evaluated at AB quantity squared. So we would find out this expression, call it D, and then that expression would have x's and y's. So we're going to put those points A, B in for x and y, and then if D is bigger than 0, if D is positive and fxx is also bigger than 0, then we have a local minimum. If D was bigger than 0 and fxx was less than 0, we have a local maximum. And then if D was less than 0, then they say the point is neither a max or a min. It actually turns out to be what's called a saddle point. What do you think of when you think of saddles? Horses. How about in math? What's that graph that we call the saddle? There's a name for it. What? Height? No. Height. Hyperbolic paraboloid. Now, if D was equal to 0, it turns out that we don't have any information about this, and so we'll need to use another test, or we can just give up and say, forget it. All right, since we found the critical points from our previous problem, let's see if we can just use that as our first example. Wait, what happened?
So why is the local minimum there?
What?
Is the critical point?
Well, it depends if the discriminant is bigger than 0, less than 0.
Those are just, we don't know if they are just critical points, that's all we know. No
Yeah.
local, no max.
All right, so let's continue on with this example, and we know that our critical point is, what is it, 1/3, negative 2/3. So what we want to do is we want to find the second derivative information. So let's find fxx. Just 2? fyy.
That one is like a
2 also? fxy.
Two x plus one. No, that's just one, right?
So fxy, which, by the way, is the same thing as fyx.
we don't actually have to plug in anything because we don't have anything to plug in.
Yeah, you don't want to plug it in, but let's just figure out what the discriminant is. So our D is equal to 2 times 2 minus 1 squared equals 3. Well, it's greater than 0, but we have to check fxx. fxx is equal to 2, and that's also bigger than 0. So we're in the first category here. So 1/3 comma negative 2/3 must be a local min. All right? Find a graph, yeah. Say it again. I don't think there's a local max. Say it again. Is there another point? -1 for x. It has to work, yeah, it has to work for both, yeah. All right, let's graph this real quick. We got x squared z equals x squared plus x times y plus y squared plus y. So we could see that the only point that looks like it might come up would be in the minimum down there. And if you plug in 1/3 and -2/3 into the function, you can get the z value. I don't feel like doing that. So there's no local max because it looks like it's just concave up paraboloid. What happened?
But we'll run into a lot of cases where there are multiple local maps, or is there only one local min and one local max?
No, there could be multiple.
There's like global max, right, too? And like global min?
Yeah.
Okay.
Mm-hmm. What happened? All right, let's see if we can do another example. Difficult, huh? I don't know.
It's got to be worked. It's got to work out. It's got to work out solution on top of it.
I'm going to run into all of these eventually, so it doesn't really matter to me. So let's take the derivative with respect to x. So cosine y is a constant, e to the x. Derivative of that is just e to the x. Derivative with respect to the y value, variable, is going to be negative sine y, and e to the x is constant. So we have to set both of these equal to 0. And let's see what happens. If we set them equal to 0, looks like e to the x equals, well, it just each of them is equal to 0. Cosine y equal to 0. So x is equal to 1, and y is equal to, well, a whole bunch of them, right? Pi over 2 plus or minus n pi. And then now this equal to 0 means e to the x is also equal to 0 and sine y equal to 0. But sine y is equal to 0 at 0 plus or minus pi n pi. So it's equal to 0 at pi, 2 pi, 3 pi, 4 pi, 5 pi, an integer multiple of pi. Wait, is this e to the x ever equal to 0? No. What? It doesn't look like there's... So I want to find when these are equal to 0 at the same time, and it looks like it's never going to be... There's no critical points here. Let's see if we can graph this and see if we can confirm that there is in fact no critical points. So it's e to the x, e to the x power times cosine of y. So as it extends further out, it looks like it still will not attain a local max or minimum. So yeah, these points keep going. So we can keep zooming out, and they go further out. So that's all we got.
Well, it is an exponential.
So what is that?
But it just
What's it look flat?
It looks flat because it flattens out. The exponential function as x goes on the negative side. It goes down, but it never comes back up on the other side, so it never takes a little dip like a bowl. It's an asymptote. I think the radical change is happening right here.
Which plane is that? The x? The y z plane?
The z is going straight up.
Oh, gotcha.
So it looks like we have no critical points here. Let's do another one with maybe a critical point. 15? Okay. That's not a good one either. You know what? Let's do another one before this one. Number 9 is only slightly more interesting. Number 10, I don't know. All right, well let's do this one then. So we need fx and fy, and we need to set them equal to 0. So chain rule or product rule, derivative of the first times the second plus the first times the derivative of the second with respect to x. So that's negative 2x. What do we have here? Big mess. We have e to the y squared minus x squared that we can factor out.
2x.
Where?
2x.
In here?
No, outside.
Oh, yeah,
2x.
the 2x.
Uh-huh.
So 2x out here?
Yeah.
minus x squared y squared. So the next one, probably going to get something similar.
Yeah, but
Everything
everything is positive.
will be positive.
Square x is 1.
So let's do it carefully. We got 2y e to the y squared minus x squared plus x squared plus y squared e to the y squared minus x squared times the derivative with respect to y, positive 2y. So this would be a 1
Plus x squared plus 1 squared.
Okay. If we set them equal to 0, for this one, we're going to get 2x equal to 0. That looks like something that's valid. And then we're going to get 1 minus x squared minus y squared is equal to 0. So that can't really solve for this, but we can say that a unit circle, each point in the unit circle, you have a possibility of getting a critical point. But it has to happen at the same time. This is equal to 0, the fy. So y equal to 0, and then you got 1 plus x squared plus y squared equal to 0, which will never happen. We have no solutions for this. So what are your critical points? So one paired up critical point is pretty clear, 0, 0. The question is that the only critical point? What else is there?
Yes, 0, 1, 0.
So you also have to pair up anything that's, as long as both of these are satisfied or equal to 0. So when fy is equal to 0 and fx is equal to 0 from here, then you have other possibilities. So you're probably going to get 2 more points. So when y is equal to 0, put that into x squared plus y squared is equal to 1. So x is equal to plus or minus 1. So now you have 2 more critical points. X is equal to 1. Y is equal to 0. X is equal to negative 1. Y is equal to 0. So now we have 3 critical points. Okay? So our problems have just begun. We got more stuff to do. And that is to find the second derivatives. So, should we keep going down on this page? So why don't I copy this fx, fy. All right, let's try to simplify this a little bit. I'm going to need to take the derivative of this with respect to x and with respect to y. So I'm going to multiply this I can leave that 2 out there. Let me just distribute the x. X minus x cubed minus y squared xy squared. So this will help me find fxx and fxy. So I have another product rule. So derivative of the first times the second plus the first times the derivative of the second. So I think that was the only advantage of distributing that, is to have the derivative of the second maybe not look so bad. See if we could simplify this a little bit. I think I only can factor out an e to the y squared minus x squared. Is that correct? Times 2. Factor that out. And then what do I have left? I have minus 2x squared plus 2x to the 4th plus 2x squared y squared minus 1 minus 3x squared minus y squared. Can I combine anything? I think I can combine those two, right? Where? No, there should be a plus. Okay. All right, so this will end up being 2e to the y squared minus x squared times, now I'm going to combine these two. I'll put it in later, so it'll be 2x to the 4th plus 2x squared y squared plus 1 minus now 5x squared minus y squared. So that's fxx. Now since we have this here, let's find fxy. Derivative of the first times the second. Oops, take the derivative. With respect to y now, this would be 2y times the second plus the first times the derivative of the second. Well, most of them disappear. 2xy. Anything we can factor? We can factor 2 and 2 and then a y. So that's 4y out. E to the y squared minus x squared, x minus x cubed minus xy squared. And then after we factor that out, this is still a negative. The 2's are gone. The y's gone, but there's still an x in there. Looks like the x might cancel. So fxy equals 4y e to the y squared minus x squared power, and then negative x cubed minus xy squared.
Where do they minus 2xy? That.
This one, the derivative of this thing with respect to y. Yeah.
And then for the first one, 2y is not minus 2x because it's
This one?
no, in the first one, down, then down.
It's a derivative of this with respect to y. The derivative of this thing with respect to y, right? Because it's with respect to y? All right. So, since we're out of time, why don't you guys finish this? No. Finish it in case it comes up on a test. What? All right. See you guys next time.
It's too long.